Welcome to a fascinating exploration of const variables, pointers, and intriguing world of Constexpr. In the realm of programming, these concepts play a crucial role in enhancing the reliability, predictability, and efficiency of your code. Join us as we embark on a journey to understand how constness and Constexpr can shape the way we build robust software systems. In this illuminating video, we'll delve into the realm of const variables, their immutability, and how they influence the stability of your code. We'll also unravel the intricacies of pointers and their interaction with const objects, followed by a deep dive into the powerful world of Constexpr variables and their dynamic interplay with pointers. Have you ever needed a variable whose value should never change? Imagine having a variable to represent the maximum number of users a system can handle. While we might want the flexibility to change this value later, we'd also like to prevent accidental modification that could disrupt system. This is where const comes in. By marking a variable as const, we indicate that its value cannot be changed after initialization. Let's take an example. Suppose we have a constant representing the maximum password length. So here I'm going to define const integer representing the maximum password length with the initial value of 32. This makes the variable max password length unchangeable. Any attempts to modify its value will result in an error. So if I try to change the value of max password length to something else, I will get an error. Expression must be a modifiable L value. Thus, for now, I'm going to comment this and write a comment that this is an error. Attempt to modify a const object. To ensure that a const object remains valid, it must be initialized when declared. The initializer can be a complex expression or a simple value. For instance, I can define a const double and name it number, and I can use the CMath library to calculate the power of 2 and 3.5. This variable is a const, but it's going to be calculated at the runtime because we are initializing it with a complex expression. However, if I define a const integer and call it weeks or days in a week, this is a const integer variable, and it's going to be initialized at the compile time because we are initializing it with a literal. So let me clarify here. Initialize at runtime. However, trying to define an uninitialized const object will result in an error. For instance, if I try to define a const bool, let's call it error flag, and uninitialize it, leave it uninitialized, I will get an error which says const variable requires an initializer. So for now, I'm going to comment this and write a comment that this is an error. Uninitialized const object. Now let's explore operations on const objects. The type of an object dictates the operations that can be performed on it. A const object can undergo most operations that a non-const object can, with one significant restriction: it cannot undergo operations that alter its value. For instance, arithmetic operations on a const int works the same way as on a regular int. Conversion to bool, comparison operations, and more remains consistent. Let me demonstrate this in an example. Let me define two constant integers, num1 with the initial value of 10 and num2 with the initial value of 5, and I can use the arithmetic operations such as sum on these variables. So this is valid. Also, I can use the comparator operator. Again, this is valid. Operations like these do not change the value of the const object, so they are all valid. Now let's have a look at initialization and copying of constant objects. Initialization plays a crucial role in working with const objects. When initializing one object with another, constness matters only for operations that can modify the object. For example, if I have a non-const integer, I can use that non-const integer to initialize a constant integer. So this is valid. Copying value into const value. And if I define a new integer, non-const integer, I can still use the constant value to copy the value of const value into the non-const variable. So this is also valid. Copying const value into new value. Here, although const value is a const integer, it behaves like a regular integer during initialization and copying operations. Now let's talk about sharing constant objects across files. When dealing with constant objects initialized from compile time constants, the compiler often replaces the variable with its value during compilation. This simplifies the code and improves the performance. However, when working with const objects across multiple files, some considerations arise. To avoid multiple definitions of the same variable, const objects are defined as local to the file they are in. Yet, there are cases when we want to share a const object among multiple files. To achieve this, we use the extern keyword. Let me demonstrate this in an example. Let's say we have a header file, and we declare the const. We want to declare our constant variable here. So let's say maximum retries. And we want to share this constant across a file. So I should use the keyword extern. And then here in the CPP file, I'm going to include the const variable.h, I mean the header file, and I can define and initialize the value of max retries in the CPP file. Like this. And if I try to build successfully. So to recap, here we define and initialize max retries in one file and declare it with extern in another file. This ensures that the variable is shared among multiple files without causing redundancy. Now let's talk about the concept of references to const variables or objects. In programming, we often encounter scenarios where we want to refer to objects without changing their values. This is where references to const come into play. If you don't know what a reference is, please watch my previous video on references. A reference to const is a reference that points to an object of a const type. Unlike regular references, a reference to const enforces the immutability of the object it's bound to. Let's illustrate this with an example. Consider a scenario where we have a const value representing the speed of light. So here I have a const, let me have some space. Here I have a const double, call it speed of light, and give it the value of 299792458. Now we can create a reference to const that points to this value. This reference ensures that the underlying value cannot be modified through the reference C. So if I try to change the value of C through the reference, I will get an error which says expression must be a modifiable value. So it means that we cannot change it because it's a reference to a const. A reference to const imposes certain limitations on how we can manipulate the object it refers to. For instance, consider attempting to change the value through the reference. So if I try to change the value of C, this will be an error. Cannot modify through a reference to const. We can see that expression must be modifiable L values. So for now, I'm going to comment this out to get rid of that error. This restriction prevents accidental or unauthorized changes to const objects, promoting safer and more reliable code. Another noteworthy aspect is that we cannot create a non-const reference that points to a const object. For example, I cannot create a double reference, which is like a non-const reference, and try to bound it to a constant double, like speed of light. This will be an error. Qualifiers dropped in binding references of type double to initializer of type const double. So this is also an error. For now, I'm going to comment this out. Now let's talk about initializations of references to const. Just as with regular references, there are exceptions to the rule that the type of a reference must match the type of the object it refers to. We can initialize a reference to const from expressions that can be converted to the reference type. Let's consider an example where we have a variable temperature representing the current temperature. So I have a variable temperature. We can create a reference to const and bind it to temperature like this. So here I am binding a const reference to a non-const object. This allows us to use a reference to const with various expressions such as literals or calculations involving the original object. Now let's talk about reference to const and underlying objects. An interesting distinction to remember is that a reference to const only affects what we can do through that reference. It doesn't dictate whether the underlying object itself is const. This is significant because the object, even if not const, can still be changed through other means. For example, if we have a non-const object count, so if I define a non-const object called count, we can create both non-const and const references to it. So here is a count reference. And I can define a const reference to it. Although const count ref prevents direct modification through the reference, the value of count can still be altered by other means. It means that it's true that I cannot change the value of count by this const reference to it. So this is an error. However, still I can change the value of count through itself. Okay, now let's talk about pointers to const objects. In the realm of programming, pointers provide a versatile way to interact with objects. Again, if you want to know more about pointers, please watch my previous video on pointers. Similar to references, pointers can also point to either const or non-const types. A pointer to const, much like a reference to const, comes with the restriction that it cannot be used to modify the object it points to. Imagine having a constant value representing the acceleration due to gravity. So I have a const double called gravity, which is 9.81. Now, if we try to create a regular pointer to this constant, like this, we will get an error. A value of type const double cannot be used to initialize an entity of type a double pointer. So this will be a error, cannot point to a plain pointer to a const object. Cannot point a plain pointer to a const object. So for now I'm going to comment this out. So this is disallowed, as modifying a const object through a regular pointer could lead to unexpected changes. However, we can create a pointer to const and assign the address of the constant object like this. I can create a pointer to a const double so this is valid. Similar to references, a pointer to const ensures that the value it points to remains unaltered. Attempting to modify the value through the pointer is forbidden. It means that if I try to change the value of gravity through the pointer, in order to access the value, I need to dereference it first. So ptr to gravity, and I try to change it, this will be an error. Expression must be a modifiable value. So this is an error. Cannot assign to ptr to gravity. This restriction preserves the integrity of const objects. Additionally, we can use a pointer to const to point to a non-const object. I know it's a bit puzzling, but let me demonstrate it in an example. Let's define a double variable call it pressure, and then try to assign the address of pressure to this pointer which we created before. So this is a valid assignment. Now you may have this question that can we have constant pointers? The answer is yes. Unlike references, pointers are objects themselves, which means we can create a const pointer. This pointer's value, which is the address it holds, cannot be changed after initialization. We denote a const pointer by placing the const keyword right after the asterisk. Consider an example where we want to create a constant pointer to an integer representing an error code. So we have an integer variable called error code with an initial value of 0, and then I'm defining a const pointer. Note that the keyword const is right after the asterisk, so when you are reading this, read it from right to left. This is a const pointer to an integer. Const ptr error code, and we give the address of our error code. So we have to initialize it. If I don't initialize it, I will get an error which says const variable requires an initializer. So we need to initialize it, and once it is initialized, it cannot be changed because it's a const pointer. Although the value of error pointer cannot be changed, but we can still modify the object it points to. It means that I can dereference the const pointer error code and change the value of error code. However, I cannot if I have like other integer, I cannot change the address of const pointer error to this one. So this is an error. Oops. It's important to realize that a const pointer doesn't dictate whether the object it points to is const. The constness of the pointer affects only what we can do with the pointer itself. Now let's talk about top-level constant. In the world of programming, the concept of top-level constant comes into play when we are dealing with objects that are inherently constant. An object can have a top-level constant if its value remains constant regardless of whether it's used. Whether it's a built-in arithmetic type, a class type, or even a pointer type, the concept of top-level constant can be applied. For instance, consider an integer variable called age. So now let's examine a pointer to an integer with top-level const. So I will define a constant pointer to an integer called p1 and initialize it with the address of age. In this case, p1 itself is constant. Its value cannot change. However, age remains mutable. Beyond a top-level const, there is another dimension to consider: low-level const. This type of const comes into play when we are talking about the constness of the objects to which pointers can point. In other words, it's about the constness of the object that pointers refer to. Imagine we have a constant double called speed. Now let's explore a pointer that can point to a constant double. We are going to define a pointer to a constant double called p2 and give the address of speed. The interplay between top-level const and low-level const becomes particularly interesting when we copy objects. When copying an object, top-level const is generally ignored. This means that copying a top-level const object to a non-const object is possible. For example, we have a constant integer ci and a non-const integer I. So let me define. We can copy the value of ci to I because top-level const doesn't affect the copy operations. So this is valid. Now let's consider low-level const in copying. The story is quite different when we consider low-level const. When copying an object, both the source and the destination must have the same low-level const qualification, or there must be a valid conversion between them. Let's take an example where we have two pointers, one with a low-level const and the other without. So this is a pointer to a const integer, and I give the value of ci, and let's define a pointer now, and let's define a pointer and try to initialize it with the value of p3. You see that we get an error. A value of type const int pointer cannot be used to initialize an entity of type pointer to integer. So this is error. In this case, copying p3 to p is disallowed because of the low-level const difference. Now let's talk about the const expression variables. In the vast realm of programming, we sometimes face challenges determining if an initializer is truly a constant expression. We might define a const variable with an initializer that seems const, only to later find out it's not. That's where the concept of Constexpr comes into play. By declaring a variable with Constexpr, we are essentially asking the compiler to validate the variable is truly based on a constant expression. Imagine we have a Constexpr variable representing the gravity of moon. With Constexpr, similar to const, we can ensure that the value of this variable remains the same throughout our program. So the only difference of Constexpr with const is that we ensure that the value of this variable is being calculated or initialized at compile time. Congratulations, knowledge seekers, for completing this enlightening journey into const variables, pointers, and remarkable universe of Constexpr. Armed with these newfound knowledge, you are equipped to create more resilient, efficient, and error-resistant code. From safeguarding the integrity of const objects to harnessing the potential of Constexpr for optimized code, you have gained essential insights that will propel your programming skills to new heights. As you continue your coding adventure, remember that constness and Constexpr empower you to build software that is not only reliable but also adaptable to the dynamic demands of the digital world. Thank you for joining us in this exploration. Keep coding, keep innovating, and keep pushing the boundaries of what you can achieve in the captivating realm of programming.